Hello, I am Hui Wen Ning, student ID 2501309. This is the demonstration video for my final year project titled Learning Interpretable Features from Histopathological Images for HER2 Classification in Breast Cancer. Breast cancer is one of the most common cancers among women worldwide. Early detection and the right treatment are critical for patient outcomes. HER2 is a key protein biomarker that plays an important role in breast cancer diagnosis and treatment. The goal of this project is to build deep learning models that can classify HER2 levels from H&E stained tissue images and help us understand how the model makes its decisions. The key research question is whether including domain-specific inductive biases can enhance prediction accuracy. The dataset used in this project is the BCI dataset, which contains paired whole H&E and IHC images. This is the original VGG16 architecture, which is used as the base model. It is often used for image classification tasks. The input image passes through several layers of convolution and max pooling to extract features, and then through fully connected layers for classification. In its original form, VGG16 is designed to classify across 1,000 categories, which isn't suitable for this task, so the classification part was modified for HER2 scoring. In the modified version, the convolutional layers from VGG16 remain unchanged. The main changes are in the final classification layers. I replaced them with two fully connected layers, each followed by ReLU activation, and added a softmax layer that outputs predictions for the four HER2 classes: 0, 1+, 2+, and 3+. These are the four loss functions used in this project. Cross-entropy. Loss is the standard classification loss and was used in all model variants. Class distinctiveness loss was added to help each class focus on distinct regions in the image, improving saliency separation. Spatial coherence loss was introduced to make the saliency maps cleaner and less noisy by encouraging smooth attention. Lastly, IHC alignment loss was used to guide the model's attention by comparing the H&E saliency with the corresponding IHC saliency map. Here's an overview of the model variants. These are the parameters used for model training. This table shows the overall classification results for each model. The performance improves gradually from Model A through to Model C. Adding CD and SC loss in Models B1 and B2 led to noticeable gains in all metrics. This confirms that including inductive biases improved in interpretability and classification accuracy. These are the saliency maps generated by Model C2. There are a few key novel aspects in this project. Firstly, GradCam alignment loss guided by IHC saliency maps was introduced in this study, which, to my knowledge, hasn't been used in HER2 classification. Secondly, different combinations of loss functions were used to evaluate accuracy and interpretability. The model was also designed to support full 4-class HER2 prediction, not just binary or 3-class setups. This project came with a few challenges. One of the challenges was the difficulty in distinguishing classes like 1+ and 2+, since they are often visually similar. Another challenge was that the saliency maps were noisy, which often highlighted the irrelevant regions. The project made solid progress. I implemented 3 custom loss functions. Furthermore, I had managed to build a system that classifies all 4 HER2 levels with interpretable outputs. Thank you for watching.